Good morning. Today's topic is single nucleotide polymorphism. See, every individual's DNA is unique. But if you take human being, they have 3 billion base pairs. But between individuals, they are 99% similar. Or it is also told that between different individuals, there are 97% similarity. Between siblings and all 99% similarity. So there are some difference between individuals. Sometimes it is referred as 1% difference. Sometimes it is told that the 3% difference, and whatever may be. This difference is actually the difference in their base pairs. Now these base pairs which are different. For example, here an individual is having AT pair, but at the same time the other individual is having GC pair. Now this difference between individuals at a particular position, that too the difference in only one nucleotide, this is known as single nucleotide polymorphism or SNPs, or sometimes it is also known as SNP. Just see here, these are two individuals DNA, individual 1 and individual 2, and you see at this position they have a variation. Each position may one individual can have any one from the 4 nucleotide A, G, T, C. The same position on another individual may have again 4 possibilities. So one of the 4 bases, and that nucleotide polymorphism is known as SNPs. It is also told that 99.9% bases are same between individuals, and 1% or 0.1%, it is said at various places, various figures, like sometimes it is told that 1% dissimilarity, sometimes it is told that 3% dissimilarity. Now here let us take 99.9% if individuals are same. Remaining only 1.1% makes that person unique. His looks, his external appearance, his internal changes, all these things are actually depend upon this 0.1% dissimilarity. The variations between individuals may sometimes harmless, sometimes it could be harmful. Okay, even sometimes it may be an advantage for the organism. We'll see what is SNP mapping. Through sequencing, we find the positions of SNP located on an individual's genome. That is known as SNP map or SNP profile. See, the SNPs are helpful in making personalized medicines. Now let us take this in detail. SNPs helps in predicting response to a medicine. Here we are taking two SNPs. You can see individual A and individual B. Both are having SNP maps, and there are some difference between their SNPs. That is positioned, or that is shown here. Now, if an individual is going to give medicine, before that we can easily check his SNP profile, and we can compare that with these two kinds. If his SNP is matching with A, that medicine will give good efficacy. If it is with B, it will not show good efficacy. So in this way, SNPs helps in clinical trials, or it helps in providing or making the concept personalized medicine. Now the SNPs, if happens in the coding region, that means the coding region is the region which transcribe and produce an mRNA and then leads to formation of a protein. Sometimes it may be silent, that result no change in the phenotype. But if it is happening again in the coding region, and if that changes the sequences, for example, the UUC become UUA, such SNP may lead to change. The amino acid changes may lead to certain diseases. Again, let us see in the coding region, if it create a stop codon, UGA stop codon, from UCA it goes to UGA, again the phenotype may change. Again in the coding region, it may affect the rate of transcription. That means up or down regulate the transcription rate is increasing as well as decreasing, which will also sometimes lead to some changes. If it happens other regions, that may not be affecting the gene product, and they are very common. And we have a lot of DNA which is junk DNA, and these junk DNA, if has some SNPs, that may not be resulting in any phenotype change, but these junk DNA SNPs are also used for fingerprinting. Our non-coding region is having very repeats in the sense the repeat of AG, repeat of GC, repeat of AGC, repeat of A, sometime repeat of G likewise. And these repeats are normally seen in non-coding regions. And suppose we take a repeat A in an individual 400 times. If any SNP happens here, now this repeat is broken into two pieces. Suppose this happens at 50th position, then you will get two pieces. 150 repeats this side, another 50 repeats here. Now we can see the length of a repeat has been changed, as well as the number of repeat also changed between individuals. This number and length change can be utilized for fingerprinting an individual. Such phenomenon is known as VNTR, variable number of tandem repeats. See, we told that SNPs may be useful or may be harmful. We'll take some examples. See here, a single base difference in the ApoE gene that is associated with Alzheimer's disease. At the same time, a simple deletion in the chemokine receptor of gene CCR leads to resistance to HIV. So आप देखेंगे तो यहाँ डिजीज होने का चांस है SNP से. At the same time, another SNP leads to resistance in HIV. So SNPs can be useful, or SNPs can be sometimes harmful. Now this table in your textbook shows different diseases associated with SNPs. First one is cystic fibrosis. Okay, at CFTR gene, if there is a mutation, lead to cystic fibrosis. Then at chromosome number 7, mutation can happen at chromosome number 7, 7q31.2, that is again a disease causing mutation. Another is Alzheimer's disease. Again we discussed it on ApoE gene. Then chromosome number 19, there is a SNP leading to disease. Codon 508 lead to phenylalanine, again a disease causing related to this. Huntington's disease, that is again on chromosome number 4. It's a increased number of CAG repeats more than 35 times due to SNPs. Migraine is also a disease which is found to have some association with SNPs. In conclusion, we can say that SNPs are helping in individual dissimilarity. They help to predict medicine response or efficacy. They lead to disease, or they may sometimes useful. The SNPs at non-coding region helps in DNA fingerprinting, and SNPs are also helping in phylogenetic studies. Phylogenetic studies means the studies related to an individual's evolution and all. Okay, so altogether SNPs play an important role in our life. Thank you.